start with radiation vector. In the radiation vector, one term is very important. This term we have already seen earlier also, which is called the wave vector or wave number vector k. Wave number vector or wave vector is a vector which is along the direction of propagation. So its direction of this vector is the direction of propagation, and magnitude of this vector is propagation constant beta. So magnitude of k is equal to beta, and this lies in the direction of the field vector or direction of propagation. Therefore, k will be in the direction of field vector r. So if that happens, its magnitude, as I told you, magnitude will be k small k, that is equal to beta. So we can write capital bold K or the vector k as k into r cap. Why r cap? Because it lies in the direction of field vector or direction of the propagation. Therefore, vector k is equal to k into r cap. Now we are doing the far field approximation. To do the far field approximation to retarded single frequency potential, we will consider a single frequency potential. Reason for single frequency, considering single frequency, is we are interested only in time harmonic field. Time harmonic fields are monochromatic. Monochromatic means it has only one frequency. And we are considering retarded field. Definitely, if you are considering a point in the far field zone or in the observation point, there whatever you are observing, its source, it has occurred at the time before the time you observed it. So it is the retarded field. Therefore, we already have discussed about the retarded field. Therefore, in the far field approximation, the potential A, vector potential A, which is a function of r, will be of this form: mu exponential minus jkr by 4 pi r. This is the amplitude part. Mu exponential minus jkr by 4 pi r. Remember this. This part, this yellow part, is the amplitude part. Then we will get A from the current distribution or from the current density. So volume integration of the current density into exponential jk dot r dash. Volume integration over the volume enclosing the source. So volume integration of this term j r dash exponential jk r dash over the volume enclosing the source. So dq r dash is the volume enclosing the source. So that is like a Fourier transform. You can see that it is like a Fourier transform. Now it has two terms, as I told you, the pink term and the yellow term. This yellow term is the non-integral factor. Now this non-integral factor has a radial dependence on r. As r increases, this non-integral factor decreases because it has 1 by 4 pi r. Also, it has the numerator has exponent form is a e to the power minus jkr. Now you can tell me from where we got the small r in the denominator. That we did the approximation. If you remember, the approximation we made is capital R. The denominator should be 4 pi capital R, but capital R is approximately equal to small r. In the denominator, the approximation for capital R is approximately small r. That approximation we have made. From that we get this denominator as 4 pi r. So this is the non-integral factor. Now look at the integral factor. In the integral factor, J current density is independent upon theta phi, because current density will be dependent on r only. But exponential jk dot r, k dot r dash, that is dependent on theta and phi. Therefore, the integral factor is dependent on theta and phi. So it has an angular dependency. So it will give us an angular dependency of the potential A. This factor, actually this integral factor, this plays important role in determining the directional properties, because it depends on theta and phi. So on the direction theta and phi, direction is determined by theta and phi. So this part plays the important role in determining the directional properties of the radiated field. The yellow part or the non-integral part can always be normalized to 1. So AR, we can always find out its normalized value with respect to the non-integral part, but we cannot normalize it with respect to the integral part, because integral part is dependent on time, theta and phi. So for different theta and different phi, the integral part will be different. So you cannot normalize that. But the first part is fixed. Once you fix the R, the first part is constant. We can normalize with respect to that. So first part is not important. Important is the integral factor. So for this we use a special notation. So AR has two factors. For the integral factor, which is important, which gives us the properties angular dependency. So for that we use a special notation Fk, capital Fk, which is equal to integration over volume J R dash exponential J K dot R dash integrated over the volume enclosing R dash. So that is what is Fk. So we are going to use this special notation from now on. We use this special notation. This now we'll define radiation potential. Fk is a 3D spatial Fourier transform of the current density. If you look, remember the form, it is integration over volume J R dash exponential minus J K dot R dash dV. So this is like a Fourier transform of the current density J. So this is the 3D spatial Fourier transform of the current density J. This depends on omega or k. Since it depends on k, k is equal to 2 pi by lambda, or k is equal to omega into root over of mu into c. Therefore this depends on either k or omega, and the directional unit vector r cap, because it is k dot r dash, therefore it is dependent on the unit vector r cap. This is completely defined by the spherical coordinate angles theta and phi. This is dependent on theta and phi. So spherical coordinate, in terms of spherical angles theta and phi, we can define what is f. So f is a function of theta and phi. Okay. And wherever it is appropriate, we indicate only the angular dependency as f theta phi. Instead of fk, we consider only the angular dependency. We do not consider the dependency on omega and k. We consider usually the dependency on theta and phi. So as f theta phi, these are called the far field radiation potential. F theta phi, this is called the far field radiation potential, which is AR is equal to mu exponential minus JKR by 4 pi R into F theta phi. This is called the far field radiation potential, and where we define F theta phi as volume integration of J into exponential J K dot R dash in the volume integration of this. So this is what is radiation potential. So this, using radiation potential, what we can find out is, we can find out only the far fields, not the near field. So since we have considered only the far field term approximation, so using this we will find out only the far field. Okay. Now let us refresh what we have learned about coordinate system earlier. Look at this. We have a coordinate system which is a Cartesian coordinate system, x, y and z. X, y is in the horizontal plane, z is vertical to or perpendicular to this plane. We have a point. From this point to the point, the vector joining the origin to the point is r, which is the position vector of the point. The vector, this position vector, makes an angle theta with the z-axis. Now from the point, let us drop a perpendicular onto the xy plane, and let that meet it the xy plane at some point. Now the point where it meets the xy plane, if I join the origin to that point, then that we call rho. So that distance is rho. Or you can also say that the projection of this vector r onto the xy plane is rho. Then from that point where the projection meets the xy plane, from that point, if I draw a perpendicular to x-axis and to y-axis, they will give me the x and y-axis. Now the projection rho, that makes an angle phi with x-axis, that is that angle is phi, it is rho and r. So now we have got what? We have got xyz, we have got r theta phi, and also we have got g, rho, g and phi. So everything we have got. And the unit vectors, you can see the unit vectors for the theta, it is from z towards the xy plane, so that is the theta cap. In the top you can see that. Then phi is from the x towards y, so that is phi cap. Similarly, rho cap is along the projection of the point onto the xy plane, that is rho cap. So this is about the coordinate systems. We have seen now three types of coordinate system in this picture. The picture shows you three types of coordinate system. One is xyz, which is Cartesian coordinate system. One is rho phi z, which is the cylindrical coordinate system. Then one is r theta phi, which is the spherical coordinate system. So in one picture we have seen this. The far field solutions of Maxwell's equations and the directional patterns of the antenna systems, they usually use the spherical coordinate system. So mostly we will be concerned with spherical coordinate system. Of course, we will use for some small time the cylindrical coordinate system for convenience. Okay. So let us come to looking at this in this manner. Let us look at a part of the coordinate system, the xy plane. In the xy plane, what we have? We have the rho vector in the xy plane, the rho vector in the xy plane, the x-axis, the y-axis, the phi. So all these we have in the xy plane. Similarly, if I consider the rho z plane, how it will see? The rho z plane will look like this. So rho z plane is a plane which is vertical to the xy plane, but it passes through the rho axis, or the rho vector. It passes through the rho vector. Then that will be vertical to this. So z axis is vertical to rho vector. Therefore, it will be vertical. So now in the rho plane, this also you can see rho is equal to r sine theta in terms of theta from this figure. You can definitely say rho is equal to r sine theta and g is equal to r cos theta. So these two you can say. So now you can say r cap in terms of rho and g, as r cap is equal to g cap cos theta plus rho cap sine theta, because rho is equal to r sine theta, g is equal to r cos theta. Therefore, r cap is equal to g cap cos theta plus rho cap sine theta. That you can find out from this figure. Okay. Then if you want to find out what is theta cap, just look at this figure. This figure gives you theta cap is equal to minus g cap sine theta plus rho cap cos theta. Why it is minus g cap sine theta? Just look at the figure. Theta is in the opposite direction of g. So g is towards from origin. G moves in the upward direction, whereas theta moves from upward direction towards rho. Therefore, that is minus g cap, then minus g cap sine theta plus rho cap cos theta. That happens automatically. Similarly, in the first figure, we have rho cap. So r cap we have got, theta cap we have got. Now what is rho cap? Rho cap is combination of two vectors, phi cap and rho cap, r cap. So that is theta cap and r cap. So rho cap will be r cap sine theta plus theta cap cos theta. That also you can see easily. Then Z cap, G cap is equal to R cap cos theta minus theta cap sin theta. So these are some relations in the coordinate system that will be useful later when we'll go to the antenna part. Next is the relationship between Cartesian and cylindrical coordinate system. Now to find out this relationship, view the xy plane and zp plane that we have already seen. X is equal to rho cos phi, y is equal to rho sin phi in the xy plane. In the zp plane, rho cap is equal to x cap cos phi plus y cap sin phi. Phi cap is equal to minus x cap sin phi plus y cap sin phi. Then replace rho and the phi cap, rho cap and phi cap. Replace the rho and the rho cap. So that we'll do by writing x is equal to rho cos phi. So from that we'll write for rho, we know rho is equal to r sin theta. So put that x is equal to r sin theta cos phi or x is equal to r sin theta cos phi. Similarly, r cap will be rho cap sin theta plus g cap cos theta. That we will write for rho cap we will write x cap cos phi plus y cap sin phi, that into sin theta plus g cap cos theta. So that you expand, once we expand that, we will get the r cap term in terms of x cap, y cap, g cap. Then x is equal to r sin theta cos phi, that we have seen. Y is equal to r sin theta sin phi, that we also know. Z is equal to r cos theta. Using this, we can say r cap is equal to x cap cos theta cos phi sin theta plus y cap sin phi sin theta plus z cap cos theta. Then theta cap is equal to x cap cos phi cos theta plus y cap sin phi cos theta minus z cap sin theta, and phi cap is equal to minus x cap sin phi plus y cap cos phi. Then let us come to the spherical length. Like linear length, if we consider a Cartesian coordinate system, there the length is linear. But if you consider a spherical coordinate system, then the length will be on this sphere. So on this sphere, the length will be spherical, it will not be linear. And now consider a section of a sphere. We have the spherical coordinate system. We have drawn the spherical coordinate system with r theta phi. So the sphere is having a radius r. So if we have a radius r, then extend r by an amount dr. Sorry, don't extend r. Keep it constant. Then extend theta by an amount d theta and extend phi by an amount d phi. So that will give us an area on this sphere at a distance r, on a sphere of radius r. So radial unit vector r cap will be completely determined by the polar and azimuth angle theta and phi. From this we can say this, because r cap ds is equal to, now this area ds will be r square d omega. This we have discussed earlier. What is the ds? ds is the elemental area, and when we discussed about solid angle, beam solid angle or solid angle, there we discussed what is d omega. ds by d omega is equal to r square, or ds is equal to r square d omega. r in case of angle dl or l is equal to r theta. Here in 3D case, ds is equal to r square d omega. D omega is equal to sin theta, d theta, and d phi. Okay. Next. So now we have considered infinitesimal length increments in each of the spherical unit vector directions, which are dl r, that is dr, and dl theta is equal to r d theta, and dl phi is equal to r sin theta d phi. These are the length, spherical lengths. The surface element ds is equal to r cap ds. Ds is equal to dl theta dl phi. I have discussed that now. So ds we can write as r square sin theta d phi, because dl theta is equal to r d theta, dl phi is equal to r sin theta d phi. So infinitesimal small lead angle d omega, which is subtended by the angle d theta and d phi cone, that will be given as ds is equal to r square d omega, using this concept of length. So d omega is equal to ds by r square, which is sin theta d phi. That we can see pictorially here on the spherical length, the dl phi and dl theta on a sphere, spherical surface, that is intending a solid angle d omega, and you can see dp is equal to pr ds or pr r square d omega, where dp is the power radiated through this solid angle. So radiated power p. Am I audible? Is it clear? Hello? Nah, down sound. Net. Hello? Am I clear? Am I audible? Nah, it's a katika utharlo. Hello?
Yes, sir.
Hello? ଶୁଭୁଛି ମୋ କଥା? କଟି ଯାଇଛି ବୋଧେ? Am I audible? No.
Huh, sir.
Okay. So then I'll start. I thought it is not audible, so I stopped. So we discussed about spherical lengths. Here we will take a break of 5 minutes. Then I will come back and we will discuss further. How is it now?